Right guys, welcome to week 7 tutorial. So today we're going through the pipe networks tutorial. So just these 3 questions here, nothing too difficult. I hope you've all gone through the lecture notes. Alright, I'll go back through and refer to some of these during the tutorial. Alright, just some key formulas that we have to pull from. Alright, so let's start. Question 1, 2 kilometer pipeline is being designed to convey 100 litres per second, so that's our flow Q. Water at 20 degrees. One proposal is for a 300 ml diameter pipe with a relative roughness of 0.002. So what is the loss of head due to friction in this pipe? Alright, so let's start with this. What I'll do is I'll take a screenshot and bring it over to the whiteboard, and then we can go straight away. Let's check them here. Righto, let's begin. So I have Q of 100 litres per second. My water is 20 degrees. My diameter, D, is 300 millimeters, so 0.3 meters. My relative roughness, 0.002. What is the head loss due to friction in this pipe? So what we need to do is we need to work out our Moody diagram, which means we need our Reynolds number, and we're given our relative roughness. So what I need to do is I need to calculate my V first. Alright, so what I can do is V equals Q on A, which equals 100 10 to the negative 3, pulls back to meters cubed per second, pi d squared, that's times all over 4, and this punches out to be 1.415 meters per second. Alright, so now that I've calculated this, I can calculate my Reynolds number. Remember, my Reynolds number is the velocity times by rho times by the diameter all over the dynamic viscosity. Now I need to find my dynamic viscosity, so what I can do is come back to lecture 1, fluid properties. In the appendix I have some viscosities here. My water is 20 degrees, so I have my dynamic viscosity of 1 times 10 to the negative 3. We can alter the density as well if you would like to, but what you're going to find is going to be very close to the same answer anyway. So 1.415 times 1000 times, this can be 998 if you would like. Both will be correct. Diameter 0.3, dynamic viscosity, which was from that appendix. And what we end up with is our Reynolds number of 4.25 or 245, sorry. Times 10 to the power of 5. Okay, we can round this up to 2 significant figures, so 25 is okay. It's probably better actually for the Reynolds. Makes it easier for the Moody diagram. So now what we have to do is we have to go to our Moody diagram, which is, have we got an appendix here? Nope. Let me just open one up. Oh, that was a bit much, Nathan. See guys, this is what I'm saying about my laptop being all over the shop. That's okay. Look, we've got reinforced concrete design for all of our water lectures. Anyway, rotate so we can see it. Alright, so what do we have? We've got 0, 0, 2, which is here. So this line here is what we're following. And we have 4.25 times 10 to the 5 for our Reynolds number, which is somewhere in here. So we come up to where they meet, about here, and then we come straight across. So once we've come straight across, what we're going to find is we have a friction factor. F is 0.024, and that's from Moody. Once I've worked out my friction factor, that's from last week, I can work out my head loss. HL is F L on D V squared on 2G, which equals 0.024. The length is 2 kilometers, so L is 2,000 meters. Times 2,000 all over 0.3 times 1.415 squared on 2 times 9.81. Therefore, the head loss due to friction is 16.33 meters. Alright, so this here answers A. Alright, so we've just solved A. So the answer to A is 16.33 meters. Cool. Now let's clear this again. Alright, let's solve B. What would the loss of head due to friction at the design flow rate if an identical pipe were laid parallel with the first one over a kilometer of the pipeline? So what we have is we have a kilometer here. We then have it being split into parallel for another kilometer. What we're trying to work out, if we have point A, B, C to B. Trying to work out the friction and see how much head loss putting them in parallel actually saves us. So what we're going to do is we have obviously a Q coming in here of 100 liters per second. So 1,000 meters with a diameter of 300. Now we've got an identical pipe, which means here is 300, here is 300, and it's also 1,000 and 1,000. Alright, we have pipe 1, 2, and 3. So now I need to solve this. Alright, what I want to bring our attention to is just these formulas here. So this is our pipes in parallel. Alright, so our flow rate is velocity in pipe 1 times the area in pipe 1 plus the velocity in pipe 2 times the area in pipe 2 and so on and so forth. But the losses between 1 to 2 is equal to the head loss in pipe A, which is equal to the head loss in pipe B. Alright, so between 1 and 2, this is pipe A and this is pipe B, the head loss in pipe A is equal to the head loss in pipe B. Alright, so just be aware of that. We're going to be using these two formulas here. So what do I have? My head loss is equal to, because this here can be seen as pipes in series and pipes in parallel, the water flows between A and B, which means I have a head loss between A to B, and then I also have a head loss between B to C. Alright, so we add the friction loss from here to here, and then we use the other formula for the pipes in parallel. We worked out our friction loss here before, alright, which was equal to 0.024. L now changes to 1,000 meters times 1.415 squared all over 2G plus whatever this head loss here is. So now we have to go calculate this. Alright. Now, how are we going to work this out? All we have to do is I have to rework out a V, and then I have to rework out my Reynolds number, and then come back through. So to work out my velocity in these two. Alright, so velocity comes in, or flow comes in, it then splits into two, and then we've got to work that out. So velocity is equal to Q on A. Alright, there is a much simpler way to do it, but we'll go through this way to start off with. So velocity equals Q on A. Now what we get is we get half comes up, half comes down. It's the same diameter pipe, so it's the same volume, same area. Sorry, same velocity, same area. So it's safe to assume it's a 50-50 split. So Q is 50, 10 to the negative 3, all over pi d squared on 4. Alright, this here equals 0.7075 meters per second, which this here is simply half of this velocity. Split in two, we can half it. Now you can come back through and recalculate your Reynolds number, or what we're aware of is, because Reynolds is equal to rho velocity diameter on viscosity, what we've done is we've just halved our velocity, so we can just half our previous Reynolds number, alright, which ends up with 2.125 10 to the 5. Alright, so this is just half the Reynolds number from before. Now what I'm able to do is I can calculate my friction factor using Moody. 0.0025? No, 0.25. That's from Moody. My relative roughness is the same. My Reynolds number has shifted, so down a little bit, comes up to where they meet, and it runs along that line, and it meets 0.25. So now I've got friction factor. I can calculate this, which is, so my head loss from A to C is equal to, we can just calculate this here, which is going to be a bit quicker, which is 8.17 meters plus, that is this chunk in here, plus this head loss, 0.025, L, which is 1,000, all over diameter, velocity is halved, 0.7075. And this chunk here, punch that in, ends up being 2.13. So what we end up with is the head loss due to friction is equal to 10.3 meters. So this here, what we can see is this is 10.3 meters, whereas before it was 16.33. So by splitting into pipes in parallel, we've actually got a huge saving of our potential energy. We've stopped losing about 6 meters of head loss. Alright, it's a huge difference, and it really does help to put pipes in parallel. So you can justify the additional cost sometimes. Alright, so that's one way that we can reduce the amount of losses, is by putting pipes in parallel. Right, so that is part B done. Let's clear this again. Alright, 7.22. This one's a bit trickier. Again, not too bad. Let's come here. So 600 ml pipeline branches into 2 pipes, 300 and 450 pipe, each of which is a kilometre long. They're rejoined to form a 600 ml pipe again. 850 litres per second flows in the main pipe. All pipes have a friction factor here. How does the flow divide between the 2 branches? So this here is a bit tedious, a bit mathematical. Alright, but what's happening, let's draw a little diagram. So 600 ml pipe comes in, splits into 2 pipes, comes back and rejoins to a 600 ml pipe. Draw with blue, so 600 diameter, 600 diameter, this is 300, a kilometre long, 1,000 meters, Nathan, 450 diameter, and a kilometre long. Cool. Now what do I know? So I know my Q coming in is 850 litres per second. I also know my Q going out, because we can't lose flow, is 850 litres per second. So pipe 1, 2, 3. Work out the flow in pipe 2 and pipe 3. Alright, so let's start. Let's calculate all of our areas first. So my area for pipe 1, area for pipe 2, area for pipe 3. Pi d squared on 4, and so on and so forth. Alright, A1 is 600 ml diameter, 0.2827 meters squared equals. Alright, so putting in D of 0.6, putting in now a D of 0.3, I get 0.0707 meters squared, and then for a D of 0.45, 0.159 meters squared. Alright, okay, so what else do I know? I know my flow coming in is 850 litres per second, so my velocity in pipe 1, so V1 is equal to Q1 on A1, so 850 times 10 to the negative 3 to bring it back to the meters cubed per second, divided by A1, 0.2827. This here will give me just about 3 meters per second. Alright, just be aware that obviously when you punch these in, there's a lot more numbers behind them. We're rounding up, so we do get some minor discrepancies between these numbers. Alright, all that is due to rounding error. Alright, so I've worked out my V1 coming in. Now, what do I know? So, from my continuity equation, my Q1, so my flow going in, is equal to my flow in pipe 2 plus my flow in pipe 3. Okay, that's something that we know. Now, the next thing that I know is if I break these down again, my Q1, my 850 liters per second, so my 0.85 meters cubed per second is equal to V2 A2 plus V3 A3, because Q is V on A, sorry, Q is V times A. So I'm just breaking these down into a more detailed formula. Now, in this equation, I know A2 and A3, and I know Q1. So what's going to happen is I'm going to end up with a simultaneous equation for V3 and V2. So, therefore, 0.85 meters cubed per second is equal to 0.0707 V2 plus 0.159 V3. This here is going to be equation 1. We're going to use this. Alright, we've got two unknowns. We're going to basically rearrange, get one in terms of the other, punch it back into here. Right, now what else do I know? Coming back to this formula here for pipes in parallel, my loss in pipe 1, my loss in pipe 2 is equal to my head loss in pipe 3. So, therefore, head loss in pipe 2 is equal to head loss in pipe 3. Now, break this formula down again. What is my head loss due to friction? Friction factor, L on D, V squared on 2G, 2, 2, 2, 2, is equal to my friction factor in pipe 3, the length of pipe 3, diameter of pipe 3, velocity in pipe 3 squared, all over 2G. Now, from the question, my friction factors are all the same. These two cancel out. 2G's will cancel out. My length is the same, they're both a kilometer. So L2, L3 cancel out. So therefore, what I'm left with is V2 squared all over D2 is equal to V3 squared all over the diameter of pipe 3. Now, let's rearrange these and group our like terms. And then what we're going to end up with is therefore, so you can cross multiply, I'll end up with V2 on V3, both of them squared, is equal to diameter of pipe 2 divided by my diameter of pipe 3, which is equal to 0.3 on 0.45. Now, if you square it, so this equals 0.66, I think. All right. So if we square it, I end up with V2 on V3. Which equals 0.8165. And now what I'm able to do is I can bring V2 in terms of V3. Alright, so now we're rearranging a bit of maths here. So V2 is equal to 0.8165 V3. This here is our equation 2. Okay, so I hope you're all familiar with rearranging some algebra here. Alright, it is important. If you go through and do a bit more water design, you will need to be doing this a fair bit. Okay, so breaking down formulas, rearranging, inserting, and then creating our equations to run with. So now what I'm going to do is I'm going to insert equation 2 into equation 3. Into equation 1. So what I might do is just rewrite them. Actually, I might be able to copy paste them. Let's do that a bit quicker. Yeah, that'll work for now. Just chuck them over here. I know that's where your snip tool would be a bit easier, but this works for now. The other is a lasso, that's okay. Should use that. Oh. Hindsight and future knowledge. Okay. Equation 1, equation 2. So now what can we do? So let's insert equation 2 into equation 1. So therefore 0.85 equals, so all I'm doing is I'm going to sub in V2 wherever V2 is. So V2 is equal to this, 0.0707. Instead of V2, I'm going to chuck in the actual value of V2, 8165 V3 plus 0.159 V3. Therefore, multiply this and then add this. You end up with 0.85 equals 0.2167 V3. Okay, so remember, multiply out the brackets first and then add in because they're both in like terms. So once we've done that, what we end up with is now divide 0.85 by 0.2167. We get V3 by itself. It's equal to 3.922 meters per second. Okay, so we've now got this here. Now I've worked out my V3. Now I can reuse equation 2 and I can work out, therefore, using equation 2, V2 equals this here, and now I can sub in for V3. V2 equals roughly 3.2 meters per second. Just from rearranging, creating new equations and subbing in, we've just solved V2 and V3. So just solved two unknowns. Therefore, what to try to work out? Alright, if we come back to the main question here, how does the flow divide between the two branches? So I want it in terms of Q. Alright, Q in pipe 2 is equal to V2A2, 3.2 times my area I calculated before, this one here, 0.0707. Let's bring it back to liters per second. I end up with 226.24 liters per second. Q3 equals V3A3. Punching the numbers again, we end up with 623.6 liters per second. And our solutions, 620 and 230. Alright, 623.36, and okay. So you'll see the difference between the two is the difference of the numbers we're getting up there, and that's just due to our rounding error here, okay. Alternatively, you could have used the iteration process we went through on Tuesday, and you would have ended up with exact results for the more iterations that you've gone through. Okay, but these here are correct. Alright, these here, the error difference or the error margin is just due to our rounding error, or our rounding differences. Okay, so they're still okay. Alright, so I hope that makes sense. Like I said, this is tutorial really only. We won't need to do much of this in our exam. Parts of it you will. Alright, especially if you go through and do a bit more water down the track, you'll need to be very familiar with how to do this. Beautiful. So let's go through and do the last question here. Alright, so this last question is not too bad. So two water reservoirs are connected by 3.6 k's of pipe. The pipe diameter is 250, the water steps upstream. So we've got an elevation difference here, got a length, diameter. In order to increase the flow rate, it's proposed to install another parallel pipe. Cool, we're getting used to this now. Assuming a friction factor for all pipes, estimate the increase in flow. Alright, so what have we got? Well, let's start off with the diagram. I have one reservoir here. I have a pipe connecting in between, and I have another reservoir here. Let's go with green. Green's nice. So my elevation difference, 49.2 meters. My length here is 3,600 meters. My diameter is 250 millimeters. And what else do I know? My friction factor, I should write this here, F22. Cool. But given the friction factor, it makes our life a lot easier. We don't have to calculate Reynolds and go through Moody. So what I'll do is I'll make this 0.1 and this 0.2. That was very average. Better. So how do I start this? Well, remember the other week we went through this nice formula that lets us calculate between these 2 points. Alright, we have old mate Bernoulli. So H1, P1 on row G plus, let's go through and let's do our velocity head, B1 squared on 2G equals, so this side is equal to 0.2. Remember, we're going to have a difference in this one here. Alright, because this time, as we've built upon Bernoulli, we also need to allow for our head loss. Alright, we're ignoring valves and fittings, so there's no minor losses, it's just due to friction. So what have I got? Well, if they're open to the atmosphere, dealing with gauge pressure, these become 0. They move very slowly, so V becomes 0. So what I end up with is H1 is equal to H2 plus HL. So my losses. Therefore, my losses are equal to H1 subtract H2. Let's take this as my datum. Is 49.2 meters. Alright, now that I've got my losses, what they're equal to from Bernoulli, I can now come through and let's type in or write out this formula here. So my losses due to friction. Alright, so just rewriting this equation and building this out a bit more. My loss due to friction is my friction factor, L on D, V squared on 2G. Has to be equal to 49.2 meters. Therefore, 0.022 times by 3.6 kilometers, so 3,600 meters. So 250 mil diameter pipe. V squared on 2 times 9.81, 49.2 meters. Rearrange this to find V squared, and you'll end up with V is equal to 1.746 meters per second. So fairly mathematical, alright, but energy equation, we then rearrange this energy equation, and then we're just filling out this here for what we know the values to be, and we can calculate our velocity. So this is our starting point. Now the next thing I know, Q is VA, 746 times by my area, pi d squared all over 4, which equals 85.7 liters per second. Alright, just to bring it back, that's our Q. You can leave it in meters, meters cubed per second, that's fine, but I prefer to bring it back to liters per second. So what have we found? Alright, what have we found? We found how much is flowing between here to here. Alright, this is not allowing for this increased flow due to putting in parallel pipes. So this is the flow as it stands. Now what we can do is we can now come back through and work out what happens next. So let's come back over here. Now the next part is I have my reservoir. It's then flowing somewhere. It is proposed to install an identical 250 ml pipe in parallel with the original one over half its length. So about halfway, I end up with parallel pipes connecting into my tank. Yeah. I'll go back with the green. So here to here, here to here, it's half of 3.6 Ks. Alright, so pipe 1, 2, 3. They're identical, so they're still a diameter of 250, and they're just at half its length there. Okay, that's what it's telling us here. Same diameter over half its length. Work out the increase of flow if I have pipes in parallel like this. So, how do we do this? Alright, just like before, what we end up with is pipes in series and pipes in parallel. So my head loss due to friction, it's not HC, it's HL, it's equal to my head loss due to friction in pipe 1 plus my head loss due to friction in pipe 2 or pipe 3. Alright, so if I went, it's pretty easy to do this, A, B, C. And we go head loss from A to C. So head loss from A to B plus the head loss from B to C. Again, coming back to this formula in here. Alright, from 1 to 2, head loss in A is equal to head loss in B. So we can just add them together. We add them together for our pipes in series. Okay, so what is next? Well, what we need to do is we can break these out again a bit further, alright, because we haven't simplified it the best. So we can now bring out to L, A and B, is friction factor, L on D, V squared on 2G, so for pipes A to B, for pipes B to C. Okay, so my velocities will be the same because they're all the same diameter. If you don't believe me, go back through, do your Q is equal to V on A for the system. You'll see all of the V's are the same. So which means what I'm able to do is, let's go 1 and 2. Friction factors are the same, the length is the same, diameter is the same, 2G is obviously the same. So to simplify this out, what I can do is go V1 squared, V2 squared, both of them times by friction factor times the length, friction factor, the length, times by D2G. This is my new formula. Punch in these numbers, so what we end up with is V1 squared, V2 squared, F 0.022 times by 1800 all over 250 1.81. That is, let me put my calculator, 0.022 1800. Oh, cool, easy. So this becomes 8 point, why can't I read this morning, 0.73 V1 squared plus V2 squared. Alright, this is our head loss from A to C. So it gets a bit more tricky through this stage here, but what we can see is, what we can do is we can allow V1 is equal to flow in pipe 2 plus flow in pipe 3. So we can come back to our continuity equation. So V1 A1 is equal to, looking at pipe 1, V2 A2 V3 A3. All of the areas are the same. V1 equals V2 plus V3, but V2 equals V3. V1 is equal to V2. Alright, just by going through our continuity of flow. So V1 is equal to V2. Alright. Now, if I sub back into this equation, what I end up with is HL from A to C is equal to 8.073 times by V1 squared is 2V2, sub it back in. So obviously both of them are squared. Bring the 2 squared out the front. What we do is we end up with 40.365. Obviously added together is V2 squared. Erase that. V2 squared. That's in our total. Okay. Bring these out the front. Alright, add them together, and you're good to go. So, what do we do from here? Well, that's my last from A to C. Need to work out my V2 squared, so I need to work out V2. V2 is equal to the square root of my head loss from A to C I calculated before. 49.2 is my allowable head loss. Subbing it back into this formula here, end up with 49.2. So that's what this here is equal to. This is what we found from Bernoulli, divided by what I end up with is I end up with a new velocity here of 1.104 meters per second. So this is the new V2 split between my 2 pipes. Okay, so remember it's in parallel, so flow through here and flow through here. Now that I've got these 2 here going, what I can do is I can know my total flow rate. Is equal to, because I've got 2 pipes, I have 2 of them, 2 V2 times by A2, which is equal to 2 times 1.104 times by pi d squared all over 4, which equals 108.4 liters per second. Alright, so that's my total flow rate due to the parallel pipes, because I've worked out my new flow between the 2. Now, this is the original one without the parallel pipes. So what I can see is therefore my increase is equal to my total flow with parallel pipes. That's not how you spell it, Nathan. Okay, let's just use numbers. That way I don't have to use English. My total flow due to adding in my parallel pipes, subtract my flow without them. So 108.4 subtract 85.7, 22.7 liters per second. Alright, so by adding in the parallel pipes in our system, so by adding in pipe 2 on top of pipe 3, I can increase my flow by 22.7 liters a second. Like I said, you won't have to do this in your exam, but you will need to do it for future studies and for this tutorial. Alright, so thanks guys. Any questions, I'll see you on class on Tuesday, or just send me an email. Thank you.